Okay, we're looking at the rec current circuit. By DC, I don't mean that big town, 340 miles away. Okay, at least by the way the roads run, direct current. Okay, first place, if you have two, let's say two conducting cylinders. This cylinder ends where this one starts. They have different diameters and different lengths. So they have different. Some voltage across these things. It turns out, for the reasons that you see somewhat explained in the transition problem, that reciprocal of equivalent conductance is sum of the reciprocal conductances. And it's easier. So this is reciprocal. And reciprocal of equivalent conductance is equal to the sum of these reciprocals. Okay, that could be fairly easily derived. But what that really says is then that the equal the sum of the two resistances. And I don't like people to leave the D out of conductance. Okay, it comes down to the fact that you got different voltages with the same current. Okay. Uh, the current's the same in every element of a series circuit. Now, there's a little bit of a caveat about a capacitor. You have what we call a displacement current there, but it still flows out. Okay, you could have a capacitor. But this would just be two. Right now, this is just two cylinders, each of homogeneous material of whatever lengths and whatever diameters. Okay. That's essentially what most resistors are. And you take those little resistors, you put in the circuit, and they're filled with something that will conduct electricity. Okay, but not all that well. But usually things pretty thick, thicker than your wire. So you got this short cylinder of stuff that's maybe 100 times the diameter of the wire that runs into it. So it's short, which means, well, a short cylinder is going to have a lower resistance than a long. Why? Because the long cylinder spreads the voltage out over a greater distance, and the spread of the voltage is the gradient of the voltage, which is the electric field. Okay? It's actually, electric field's actually opposite to the gradient. Okay, well, you know all that from what we've done so far. And just putting this into that context, this comes out rather simple. Okay. And you can do it with some simple equations that you read about. Don't understand them, I'll explain. Okay. This is in series. Series combination with no branch. Now, I was asked earlier about the, I mean, at the beginning class, about analogies between this and conduction of heat. Okay. Well, conduction of heat is actually a diffusion. In a sense, this is also a diffusion process, but it's one where the diffusion is almost instantaneous. And it's treated as instantaneous unless you're dealing at the nanosecond or picosecond time scale. And pretty much, so I think even at those, but I'm not sure. Okay. Analogy would be these are two cylinders that are conducting heat. They're insulated, so no heat escapes the sides, and the heat to travel through these things has to travel in a straight line. It has to travel through cross sections. Okay. And the heat flow will then be perpendicular to cross section. In that case, you have an analogy that you've got a heat current. Okay. So then what drives the heat current is the difference in temperature between this end and this end. Okay. And there's some temperature at the interface. So it's just analogous to there's some voltage at this end, some voltage at this end. And there's some voltage drop across each element so that there's some voltage at the interface. Okay. That gives you some electric field here with some electric field here. If you're talking about conduction, you have a potential gradient or temperature gradient through here and a temperature gradient through here. Temperature gradient is totally analogous to the potential gradient. The temperature is actually a potential function for the heat flow. Okay. So since everybody's literate with gradients and stuff at the level of pre-calculus, multivariable calculus, can't keep those courses. You see that there's a pretty good analogy. Okay, see, it's okay to think because we did some measurement of heat currents, and that might be something. Of course, we did some measurement of electric currents too. So, the general idea of a vector field that comes from a potential function is a great big deal. If you've been through multivariable calculus, especially the last chapter, which we're just about to enter next week in the current course, we'll get into something. Okay, and it's a big deal, and in many electric, that's in many fields: mechanical engineering, electrical engineering, civil engineering. Okay. And even engineering fields that I don't have a clue about. Okay. Anyhow, there we have this. And it's the basic rule for equivalent resistances. Okay. Then we have parallel. So it's like we have a current that comes in here, it goes through let's just say. Some cylinder here. Some cylinder down here. Okay. Conductance 1 and conductance 2, and you have the same talk about voltage drop because the electric field is in the direction of voltage drop. Gradient is in direction of voltage increase. The current flow is in the direction opposite to gradient, which is the direction of voltage drop, which is why we talk about voltage drops a lot. Okay. So, you know, that term gets thrown around a lot and not often explained very well. If you know about gradients, even at the level of the introductory problem sets, transition problems, which don't involve any calculus either. Okay. It should make some sense. You can simply say that the voltage times the conductance here is the current through this one. Conductance 2 times the voltage is the current through this one. And the current that goes in here splits into these two, but the sum of these two is the current that goes in. Okay, you know, what goes in has to come out. And what goes in here has to come out here. What goes in here has to come out here. So what goes in is a sum of what's going through here. Yes, and that's put it in accurate terms. So the equivalent conductance is conductance 1 plus conductance 2. Now just step by step there, you can think about it. And you can also derive this just, from Ohm's law. Voltage is the same, so current here is voltage divided by this resistance. Current here is a voltage divided by this resistance. Okay. And the current, the whole thing is equivalent. It is the same voltage divided by the equivalent resistance, and this pops right out. I like relating it to the conductance model and making you think about it a little bit. But in practical terms, just that is a way of understanding these rules. There are other ways you can read the book. Right there are your 2 rules. And doing that, you can analyze any circuit that's a combination of resistance elements and voltages. So for example, as a simple example, if you have R1 here, then a voltage here, and up here, to this is a series of R1 with the equivalent resistance of this parallel combination. Okay. Now this R equivalent, if you multiply both sides of this equation by the common denominator, something you should know how to do, but somehow nobody ever does, you're going to get this is just the product over the sum of these two resistances. It's a simple algebraic rearrangement of this equation. So if we have a current flowing here, current we get here is going to be the same as the current we get here. Included from this, we can conclude that the current, now assuming a ideal source with no internal resistance, because everything we do in lab, we're doing a lot of stuff with batteries and they all have internal resistances, right? You gotta take that into account and put the rest out. Okay, so using this equivalent, well, this is equivalent to voltage which is a single resistor R1 plus R equivalent. So I want to talk about voltage drops. The drop across here is negative because the voltage increases. This is negative in the positive terminal. Voltage increases. Um, Voltage drop across here. Negative V if our current is in this direction. Voltage drop here. Is I times R1 plus R equivalent. The voltage drop is in the direction of the electric field because the electric field is opposite to the gradient. Okay, that's what it comes down to. There it is. Voltage drop over here is this. So total voltage drop is 0. That's just conservation of energy. Voltage drop is the work per unit of charge. Is do a complete circuit. If you go from any point in this circuit back to the same point, you have a voltage drop of negative V and a voltage drop of I times R1 plus R equivalent. Since you're coming back to the same point, and since electric fields are conservative, there's no change in potential energy. And that's why the voltage drops are 0. Say by energy conservation, now it's leave myself enough room, so it's kind of obscuring this, and you can't read that last word, but it says by conservation, by energy conservation, and I would say, and I'll put in parentheses, the conservative nature of vector electric field, which is equivalent to the fact that energy is conserved in this electric field. And this whole thing is the result of the action of the electric field. The total voltage drop is 0. Now, some of that will get glossed over, even in your text, even though it's probably going to be explained pretty well. But I'm trying to approach this in the most general way. It's the idea of energy conservation and the meanings of current, voltage, existence. Okay. Now, from this, we then can go back up to these diagrams. We can figure out what I is, and we know what I is. Okay. So that drops are I times R equivalent. I times R1 and negative P. You multiply your current by your resistance, you get your voltage drop. Okay, in the direction of the current. So I can immediately figure out what the voltage drop is here and here. Now, since I know the voltage drop across the parallel combination, I can determine the voltage, the current through R1 and R2. Here you have the voltage drop, I times R equivalent. So that we can split the current off. Okay, current splits off here. I2 here. And I3 going through this resistor. Makes sense? We can calculate I1 or I2 and I3 very easily then. two is just I times R equivalent over R2, because I times R equivalent is the voltage drop across each resistor. Clarify, voltage drop from here to here is the same whichever path you take. Conservation of energy and all that stuff. Okay? So now we can get currents I2 and I3. Now that's a pretty simple circuit. Set one up in lab next time and measure it. Okay? Using nichrome or using industrially produced resistors that aren't as accurate. So, we'll do something like that. And really what I want to do in the lab incidentally is build a good inductor. All I got to remember to do is take my hacksaw outside, cut a section out of a 6-inch sewer pipe, not in use. Thin walled 6-inch pipe, cut a section out of the mill, wrap wire around this end, wrap wire around this end, put a bunch of metal in it, get something that you darn well be able to measure. We might even be able to put it in the circuit with a function generator and measure its response and compare with what you know about differential equations. Differential equations, of course, you solve step functions. These are Laplace transforms. Okay. Now, I'm not going to make you do that. I'm not going to put examples outside the scope of the course. But since you have the background, and some of you at least are pretty interested in that stuff, we're going to see it. Okay. You can then review your differential equations and see if you can solve those equations, which I'm sure you could have at the time of your exam. It's been over a year for one of you. Okay. The rest of you, it's been more recent. So I'm not going to test you over you now the differential equations. I'm just going to show you why you learned what you did differential equations. Might not get all that done Friday. I never get done what I think we're going to get done. Just something to look forward to. Keep yourself alive until Friday so you can do this. Then find another reason to stay alive. Okay. Like habit will develop. Okay. You get this? I mean, you see the scheme of this? The details are just trivial. Okay, you learn to do this in high school physics. But maybe you don't learn to do it in the context of energy conservation, and you don't mention gradients. Okay. Although gradients can be made, you can talk about gradients for, one-dimensional case, specific derivative. Okay. So maybe in some courses they do talk about gradients if they would be appropriate. But listen. All right. Okay, you understand that? Okay, that's what you get for, and these things get a lot more complicated, but you got to break them down step by step and put them back up. Okay. I do want to talk about RC circuits, but I'm going to continue on with resistance. You've seen Kirchhoff's laws anywhere? Does that ring a bell? Where might you have seen it in some of your engineering courses? You've interfaced your brain with AI. Did the AI mention anything about it? Is that where it came from? Or aren't you using those interfaces yet? Okay. Okay, well. Let's just draw a circle with a bunch of resistors. This circuit here is actually just this. Take this much of the circuit's in parallel with this. Okay. And this much of the circuit is just a simple series circuit, so well, actually be this in parallel with this. But you can actually analyze this in terms of series of parallel circuits. But if you do this, I'll take my word for it. Very clumsily drawn because this jump shouldn't obscure part of this resistor, but this just means you put a you build this square circuit with 4 resistors, then you put a bridge across here with a resistor in it, then a bridge across here with a resistor in it. If you do that with wires and stuff, well, this resistor will be on top of this one, or this will be on top of this one. Okay, there's your circuit. Let's say now we've got R1, R2, R3, R4, R5, R6. And then let's say we put bridge here with a 7 resistor. And then just to make things interesting, put voltage here. All the resistors. Now, if I tell you what all those resistors are and those voltages, you're going to be able to figure out how much current's flowing through each resistor, right? Well, yeah, it isn't as hard as you think it is. Okay. You have 2 rules. Total current into a node is 0. Okay, well, let's put some currents in this. Let's see, let's start fairly simple. Now, you don't know what the currents are. You don't even know what direction they are because you don't know the voltage. Like, if you get a huge voltage here and a huge resistor here, then this voltage is going to tend to push things in this way along this circle. Then if this isn't a big enough voltage, current's going to be pushed through this thing in the direction opposite the direction it's of its electric field. Okay, that makes sense. So put a big resistor here and big resistors up here, and small resistor here. If this isn't big enough, current's going to flow this way. And then you can look at other possible scenarios. Okay. So I'm going to say that we have current I1 here. Now that current is the same all the way from here to here, because there's no branching point. There's no point for there's no place for the current to go. If I've got an alternating circuit and a capacitor in there, well, that comes later. Okay, that would change. But nothing in here is going to cause this current to branch. There's no capacitor current can't accumulate anywhere. Okay. Then let's just say I think I've got a current I2 Here. Let's put a current I3 here. This is a node. And just for clarity, I'll write it as node 1, and now I can write an equation. Much current flows into node 1. And I2, the way I've drawn these, flow into this node, and I3 flows out. Now, that doesn't mean that the currents are actually in these directions. Like I say, if this is big enough voltage, it'll push the current and other things. It'll push the current this way as opposed to the way the current would go if this was the only source. Okay? That's okay. What we're going to get is we're going to get a bunch of simultaneous equations in currents I1, I2, I3, I4, and so forth. A system of simultaneous equations in currents that we solve. Okay? And it's going to be a bunch of simultaneous equations, which is ordinarily a big problem, but there are going to be a lot of zeros in it. Okay, like here, we've got I1 through I8. We've only got 3 of them here. Okay, that's going to make it simple. Now, if they get really complicated, it's just a matrix equation. You plug the coefficients of I into your matrix, press a button, and you get your solution. Okay, but it's surprisingly easy to do these by hand. It's pretty easy to see what can eliminate, what can't. Okay, so anyhow, there's node 1. Okay. Now there are other nodes. You got a node here, a node here, a node here, and a node here, right? We've got 6 nodes. I'll just use N3 for node 3. N4 for node 4. Node 5. Now I've got the current here flowing through R1. Let's call that I4. I've got a current I5 R5. And you don't try to, there's no need to contrive to have the subscripts of your currents matching the subscripts of your resistors. You can if you want. And there might be a point to it sometime, might help you organize it, but it's pretty much unnecessary. Okay. So you just don't really worry about it. You just put currents where there got to be currents. So here's an I6. I7. Now, do I have an I8 here? Well, this wire jumps over this one. There's no node between here and here. So that I5 acts all the way from here to here. Okay. And I should have drawn this a little bigger, but that's all right. It's not hard to see how to do this. And given that everybody's been through linear algebra, it shouldn't be at all difficult for you to solve the equations. Even to write the equations in augmented matrix frequency. Okay. As I say, a lot of stuff cancels out quickly. It comes out pretty easy. Okay, so we've got a current I8 here. Now, have I got current for every resistor? I think I do. Now, if I had two resistors in here, an R5 and an R10, say, I6 would still go through both of them because there's no branch point, right? Okay. So we've got this equation. Now, I'm not going to write out all these, but I'm going to go to, I don't know what node do you want. Let's just go to node 3. Let's go to node 2, which is good. I have to list them in order, but when you decide how to number your nodes and how to number your loops, okay, you can work it out if you will. Okay, node 2, what's your equation for node 2? Can you write down the equation for node 2 real quick? There's node 2. What goes into node 2? Well, you don't see anything going into node 2 here, do you? But between here and here, there's no branching point. You got I2 down here. So you got I2 here, right? So if you're looking at what goes into the node, take one branch and follow that branch until you see a current. And if you don't see a current, then write one in. Don't write extra currents, and don't write an I9 here and an I2 here. So we're going to say, it actually looks to me like all of these currents are going out of the node. So if I want to write this carefully, I would write, I would start lining these up. I'd write minus I2, and then I'd have minus I4 and minus I6. I put minus I4 here, minus I6 here, and that would equal, then I'd leave myself room for I7 and I8, and I'd put equal 0 over here. And then I'd rewrite my equal 0 here. I'd move it way over. I don't have room to write it out there. But you see, I'm leaving myself room to leave the I2s in a column, I3s, I4s, because you're going to want that. Because you're going to be able to add multiples of equations to others and lift it. And it's much easier than it looks like it will be. I'm not going to work this one completely out. But you see, we got 5 nodes. Okay. How many currents do we have? 8. There's 8 variables. We're only going to be able to get 5 equations from the nodes. Okay. We need 8 equations. It is not that complicated a circuit. Well, it turns out it's easy to write them, but then got have nodes 3 through 5. Now, need something else. Just drop around any loop to 0. Well, you see any loops in this circuit? There are all kinds of loops in this circuit. The loop is I start at one point and I end up at that point. Okay. Well, starting at this point, I could do a loop from here to here to here, back up to here and back. The voltage drop around that loop is 0. I could start here, go down through here and go around the whole thing and come back. That'd be another loop and the voltage drop would have to be 0. Okay. Now I could then do a loop starting here, going around. Okay. And the voltage drop would be 0. But if I did the loop here and the loop here and the whole loop, I can see that the loop around the whole thing is a linear combination of this loop and this loop, right? So I get nothing new. So if I did this loop and the whole loop, I wouldn't do this loop. Because this loop is just whole loop minus this loop, okay? And if I did that, I get a bunch of equations I couldn't solve. Okay? They'd be consistent, but you wouldn't eliminate all your variables. So I'm going to say loop one. My voltage drops. Well, I'm going this way. So as I go here, my voltage drop from I8 would be positive, right? It'd be I8 times R4. So I could do that. Okay, I'd have I8 R4. Leave this thing in there yet. Okay. I would have I3 R7, but it's in the direction opposite my path around the loop. So I would have actually I'm going to put R7. This one's positive, that one's negative. And then the only other voltage drop I have is here. And what would my voltage drop from here to here? Both the positive and negative. The voltage drop is, so I didn't put this in, but this is V2. So I'd also have a plus V2. Okay. Now, if I go around, say I'm in a loop and I go through this voltage, there's a voltage, negative voltage drop. Okay, it's not the voltage change, it's the voltage drop. Okay, the voltage change here is positive V. The voltage drop is negative V. Okay, now I've got the plus V2 equals 0. It turns out I'm going to want my voltages on the other side of the equation. Okay, well, that's my equation for loop one. Now we need two more loops because we need 5 equations. We will get a loop from each node, and you want to do that, okay? Because they're the easier ones to write. What other 2 loops do I want? Well, I could do this loop. That's a nice one. I could do this loop. Do this loop. Okay. Or I can do a loop around the whole thing. I'm going to say loop 2. It's the outer perimeter, the way I drew this. So for loop 2, yeah. For here in the end, I'm going to get a minus V2. Not with an equal sign. It's going to be a voltage rise, which is a negative voltage drop. I'm going to run that loop in this direction. That's just a characteristic of the direction I chose. Then I'm going to have plus V1. If I'm going around this loop, my voltage is dropping. Okay. Then I'm not running into any resistors until I get here. And I'm gonna have I6R3 or R2. See, that was R7, wasn't it? Two. So I'm gonna have a R2I6 and an R3I7. That's all I got going around. There aren't that many elements. And oh yeah, I missed the R8. R8I1. And that would then be equal to 0. But instead of writing equal to 0 when I got voltages in there, I go ahead and put my voltages on the other side. Now you see, I'll have 8 equations, but a lot of these variables are easy to eliminate. And then you just use what you already know how to do to eliminate elements of an equation. Okay, I got a question here, so let's see what it is. Yeah, we have Donald Duck in one, Boris Karloff in another, and somebody suggested Foghorn Leghorn. Bugs Bunny, John Affleck, uh, whoever you want. Okay. Question was, by using this big loop, am I not doing a linear combination of 2 other loops? Well, that's not the way it was phrased. The confusion is this loop is part of the big loop, but the big loop is not a linear combination of any other 2 loops. If I use this loop here as well as this loop, then the big loop would be a linear combination. Okay? Because this loop plus this loop equals whole thing. So you got to be careful about that. Now, I haven't written out a complete set of equations, and I'm not going to demonstrate how to solve them because everybody in this course has been through linear algebra and polynomial calculus, differential equations, and all that. You can certainly solve a system of 8 linear equations and 8 unknowns. And you know how to write it as a matrix equation. So if you got a much more complicated circuit, you're probably not going to do it by hand, but it's surprisingly easy to do this by hand. Now, I don't have numbers in here, so you don't want to try to do symbols, but you can put numbers in these resistances. You can put numbers in your voltages. Okay. And then solve it. You just start eliminating variables. That's all there is to it. If you got an I1 here and an I1 in the equation down here and no other I1s, then you're going to be able to eliminate I1 real quickly. And it turns out that one by one, you eliminate the variables without much trouble. It's hard to draw a circuit, it would be really difficult to eliminate variables. Okay, now I want to talk a little bit about RC circuits. And let me just pause and see what else I might be forgetting to talk about. Okay, now capacitor into this circuit. But you don't want to deal with that right now. Okay. Because it turns out as soon as you throw a capacitor into a circuit, it's not a direct current. You might have a direct current source, okay? But you don't have a constant current. So the simplest circuit is just got a capacitor. Got a Here. Resistor here. And you got a current. I. Then you got a switch. So you got to put the switch in. So initially you have no current. Now we've been over this, talked about it in lab. I think we even talked about it in class some. What happens when you throw the switch? Well, this is the positive terminal. Okay. It's going to trap negative charge. So negative charge is going to suck off of this plate of the capacitor, this molecular subregion or whatever it happens to be. And positive charges, well, negative charge is going to be pulled off here. Okay. And the battery is then going to push them through to the positive plate, which repels them onto here. Okay. As a result, this one is going to end up positively charged because you pulled negative charges off of it. And this is going to end up negatively charged because the negative charges that get pulled off of this one, they get pumped through the battery chemically. If this is some kind of rectified generator, like the crank generators we use, then the electric field that's created there will create a voltage around a loop, so forth, and do the same thing. So you got some source here that's constant voltage. Then if the charge of the capacitor is Q, the voltage is what? Well, remember, capacitor is the amount of charge you store per volt. Okay. There's your definition of capacitance, and you conclude that it's multiplied by V and divided by C, that V equals C. So let's just make a note that capacitor is Q over C. This thing in parentheses just reminds you of the definition of capacitance. Big capacitance, you can put a lot of charge on it without much voltage. So big charge over little voltage is big capacitance. And then, of course, the bigger your capacitance, the less voltage you have for a given charge. Okay. The more charge you need to get a lot of voltage. Then you want to kind of make that intuitive, at least something you remember to think through every time you think about it. Okay. So what's your current? The resistances are capacitor C, your voltage is the not sure where I stopped recording. I didn't when I started doing the capacitors, so let's just kind of recapitulate that real quickly. Got a capacitor in series with a resistor and a voltage. The charge of the capacitor, we're gonna call Q. Now, this differs from your text a little bit. Your text kind of calls capital Q something else, and you got this small q of t. But anyhow, if the charge on the capacitor, actually, let's go ahead and change that. And we're going to put the t. Actually, maybe I'll represent kind of like that. Okay, so charge of the capacitor is Q of T over C. It's just because, you know, capacitance is Q over V, so voltage is Q over C, whatever Q happens to be. If Q is Q of T, that's what you get. So now we have this for the voltage of the capacitor where Q of T is Q of whatever time you're looking at. Current is I equals what? Well, use the loop. The loop, the voltage drops. If the loop goes in this direction, the voltage drop here would be negative V. Then I'm going to use lowercase q here. Adding that lowercase q means Q of T. And there we have the loop equation. Okay, go around the loop. Voltage drop here is negative V because the voltage rises. Voltage drop across the capacitor is Q over C. Voltage drop across resistor is IR. So I equals this, which just comes from solving this equation for put all this stuff on the other side and solve it. And you get V over R minus Q over RC. Okay. Now, yeah, Q is a function of T. I'm very used to even capital Q there. Overcome my tendency. Okay. Just to be consistent with the text. I is dq dt. I is V over R minus Q over RC. So I is dq dt minus V over R minus Q over RC. So Q prime, which is your dq dt, plus your Q over RC equals V over R. It's a differential equation. We solve the homogeneous equation, Q prime plus Q over RC equals 0. We get dq dt equals negative Q over RC. This is a separable equation. We can also solve it using the Pyle solution. Q equals some constant times e to the RT. And we're going to get a complex solution of that and get a real space. Then it'll work out the same. But I'm going to solve as a separable equation because that's something you actually see in simple cases in calculus 1. Okay. So rely on the differential equations knowledge as little as possible. So we have Q prime plus Q over RT equals 0. It's a separable equation. You could write as dq dt equals negative Q over RC. We separate out get dq over Q equals negative dt over RC. Leading very simple steps. The natural log of the absolute value of Q is negative T over RC plus alpha, which is I'm using for the integration constant. I didn't want to use a C because we got the C for capacitor. I want to use K because that's often in the exponent of an exponential. So I'm just using alpha, and it's not going to be very long. We solve this, and we get Q equals e to the negative t over RC plus alpha. If you get a natural log of Q, it's equivalent then to saying, that Q is e to the whatever, by the inverse function, so forth. That should be very familiar, especially if you've had differential equations. Even if, you know, you had any calculus course. So we get this, and then the e to the negative t over RC plus alpha, e to the alpha, e to the negative t over RC, meaning e to the alpha can be any positive number. Okay. Now, since your charge could be negative, we note that since we have an absolute value around the Q, get here is actually a plus or minus this. So now we get the homogeneous solution, Q equals AE to the negative T over RC. That would be a positive Q, that would be our Q of T. But that's the homogeneous solution. A particular solution, that means we just have to find one solution to this equation that works, and we add it to our homogeneous solution. And the particular solution, it's using lowercase q over here. Q over RC would equal V over R. Where Q is a function that satisfies this equation. If Q is just a constant function, constant Q, then Q prime is 0 and Q over RC would equal V over R. That's what I've got here. In particular, there's our particular solution, QP equals CV. So our solution could be P equals CV plus AE to the negative T over RC. Now, CV, capacitance, is charge over voltage. CV is the charge on this capacitor when its voltage is the same as the voltage of the source. Okay, so if voltage is total voltage of the source, which is the case here, CV is then what I'm going to call max. And for A, I'm going to use minus Q max without too much explanation. Think it through. And here you have the charge on a charging capacitor as a function of time. Now this assumes that the capacitor started out on charge. Q max let's see, and there it is. Your current would be the derivative of this. Now this term goes away, and you get E the negative T over RC. Your text will explain that in a little more detail. And maybe even a little more color and a little less reference to differential equations. Okay, but there we have it.